Hello, my name is Saptashri and I shall be presenting our term project CISCO Compute-In-SRAM macro for position and encoding using CORDIC algorithm. The motivation for this work comes from the fact that LLMs are becoming indispensable due to their capability of understanding and generating human-like text. However, they consume massive amounts of energy, primarily due to the energy-hungry data transfer between memory and processor in a von Neumann architecture. The solution is to compute within the memory, which comes in two forms, analog SIM and digital SIM, each with its own overheads. While analog SIM is energy efficient and compute efficient, it has its own non-ideal effects. And digital SIM is highly accurate, yet it is bulky and has energy overheads. So we use a hybrid approach which provides the best of both worlds, where certain operations are performed in the analog domain while certain in the digital domain. Now coming back to the question of accelerating LLMs. So what are the operations of an LLM that needs to be computed in memory? Turns out that we can compute the most frequent operations like MVM, softmax, and position encoding for efficient LLM inference. So far, most works have been focused on accelerating MVM and softmax, so we turn towards position and encoding. So LLMs are by default permute invariant, means that a sequence dog bytes man and man bytes dog are rendered the same. So we need to inject the information of position of tokens within a sequence so that it is able to distinguish between the two. As can be seen from the equations that computing quantities like sin theta and cos theta are essential for position and encoding, traditional schemes uses a lookup table containing thousands of rows having pre-computed angles, and the lookup table is used to interpolate and find the value of sin theta and cos theta for unknown angles. This requires the use of complicated digital multipliers which are energy hungry, consumes a large area. Additionally, storing such a bulky lookup table consumes a lot of memory. So we instead use the CORDIC algorithm, which is a set of iterative equations based on addition, subtraction, shift operation, and it uses a near zero LUT having just 7 to 8 rows. So in CORDIC, we begin with a vector along the x-axis and we rotate it in terms of fixed angles towards the final target angle. These fixed angles are known as CORDIC angles alpha I, which are of this form. The first 5 CORDIC angles have been shown in the table. This is the algorithm through which, after all the CORDIC angles have been used to rotate the vector, we get the value of cos theta and sin theta. So we need a control of the rotation, whether we need to rotate in the clockwise or in the anti-clockwise direction. It is beta which controls the direction of rotation. If the present vector has already surpassed the target angle, then we need to rotate it clockwise. And if the present angle is short of the target angle, then we need to rotate it anti-clockwise. So in this work, we have designed SRAM, store the internal variables, a reconfigurable in-memory adder subtractor, an in-memory shifter, a SRAM based ROM to store the LUT, and a multibit comparator. And then we have integrated all the blocks to complete the coding, same macro. SRAM has been used as the memory element because this is an iterative application wherein we need multiple read and write cycles. SRAM being faster as compared to DRAMs and NVMs will be able to provide high throughput. Specifically, we have used an empty SRAM because it has separate read and write ports, which leaves the internal storage nodes undisturbed, which is crucial for the shifting block where multiple cycles of read and write are taking place. So the iterative equations of xi, yi, and epsilon can either be addition or subtraction depending on the value of beta I. So we need to have reconfigurable adder subtractor. We begin with the design of in-memory full adder, uh, which uses NMOS-based discharge paths to compute different logical operations between the inputs, and these are you then combined using digital logic to compute the sum and compute output as shown. Now we need to extend the structure of subtraction as well. We observe one important phenomenon that subtraction a minus b is nothing but addition in the ones complement form. Now b comes from an SRAM, and an SRAM stores both b and b bar. So it remains only a matter of choice whether we feed the read bit line, the complement of the read bit line, and feed it to the adder. This is done with the help of a mask, with beta as the select line. After that, we have the in-memory shifter, which has two sets of SRAM, an upper bank and a lower bank. The upper bank stores the value of xi, and the lower bank gives us the 1-bit right-shifted operation. The read bit line of the lower bank is then fed back to the write bit line of the upper bank, and the cyclic rotation continues in this way. Each rotation takes 2 clock cycles, so an I-bit right shift will take 2I number of clock cycles. Here is the timing diagram showing the read and the write word line signals of the upper and the lower bank of SRAM. And these are the time windows where we get 1-bit, 2-bit, and 3-bit right shifted operations. We also need a multi-bit comparator which will compare the residual angle epsilon with 0 at every iteration to determine the next value of Bi. Here we have used behavioral modeling of the comparator, keeping in mind the goals of the project, and a 12-bit comparator has been designed over here.
Hi, I'm Vishnu Priya. I'm going to continue the presentation from here. The LUT-RAM provides a direction of rotation that is used to update the xi via vectors and the residual angle epsilon I. The LUT-RAM computes the below two equations. It computes the residual angle and gives the direction. The LUT-RAM has the following components: an angle SRAM bank to store the 5 predefined angles. In this design, we have chosen to use 5 iterations. Apart from the SRAM bank, there are 3 SRAM row buffers that are used to store the intermediate values during the iterations. Each SRAM row here is a 1280 cells. Along with these, there's a comparator and a reconfigurable adder subtractor component. The angle SRAM bank contains 4 SRAM rows, and each SRAM row has 1280 SRAM cells. All the 5 SRAM rows are having a common bitlines for the write and common read bitlines as well. Each row is used to store each predefined angle. The read bitlines are having a common precharge and the sense amplifier circuit connected to it. These circuits are enabled only during read operations. The SRAM bank is treated as a RAM structure because we initialize them at the start of the simulation and we don't actually do any write during the CORDIC operation. Coming to the execution part, let's start with the initialization process. The angle SRAM bank has to be initialized with all the 5 predefined angles, and the alpha C buffer holds the current residual angle, current predefined angle used during the iteration. The epsilon I plus 1 buffer and epsilon I buffer are initialized with the target angle theta. The mux here selects one among the initial angle or the computed epsilon I plus 1 during the iterations. The execution is performed in 3 stages. In the stage 1, it's a comparator stage where we compare the residual angle against 0 to figure out the direction. In the stage 2, we update the residual angle using the current residual angle from the epsilon I buffer and the predefined angle picked from the alpha C buffer. And the direction is picked from the comparator output from the previous stage. And the epsilon I plus 1 is updated into the epsilon I plus 1 buffer. In the third stage, it is writing back the epsilon I plus 1 buffer into the epsilon I buffer to make it ready for the next cycle. At the same time, we update the alpha C buffer with the predefined angle that is used for the next iteration. As we can see here, the stage 1 and stage 2 happen in the consecutive cycles, but the stage 3 has some delay factor added to it. This is to accommodate the delay during the shift register operation for computing xi and yi vectors. Below are the results that are shown for a target angle theta, which is 60 degree that we have picked. In iteration 0, the epsilon I is updated with 60, which is the target angle. And all the alpha i's are constant for a CORDIC iteration. For any CORDIC algorithm, these alpha i's are constant. In the iteration 0, since the residual angle 60 is greater than 0, the direction remains positive, and the epsilon I plus 1, xi plus 1, and yi plus 1 are computed using the direction of this. In the next iteration, the epsilon I, which is residual angle 15, again it's positive, so the direction continues to be plus 1. In the iteration 2, the direction changes because the epsilon I value is negative 11.6. In the third iteration, the direction again comes back to positive because the residual angle is 2.4, which is greater than 0. And in the iteration 4, the epsilon I is negative 4.7 and therefore the direction changes. The same outputs are observed in the simulation analysis. If you see here in iteration 0, The epsilon I is 60, therefore the beta is positive. So in the simulation, the assumption that we have made is if the angle is greater than 0, then the beta I, the direction is positive 1. But if the angle is negative, then the beta is marked as 0. If you see in the iteration 1, the epsilon I is 15, which is positive, and therefore the beta is 1. In iteration 2, the epsilon I is negative 11.6, therefore the direction became 0 here. And iteration 3, epsilon I is 2.4, which is positive, and I is equal to 4, which is iteration 4, therefore epsilon I is negative 4.7, and the direction is changed here. We have evaluated the angles not just for 60, we have evaluated it for 27, 33, 60, and 75. And the percentage error that we have seen for sine theta and cos theta for each angle is mentioned in this table here. On an average, if you see the computation of sine theta and cos theta, the error average is 4.2%, 4.02% for sine theta and 2.3% for cos theta. Overall, the accuracy of CORDIC macro is close to 96.84%. And the time period that we have picked here is 10 nanoseconds, and the throughput that we're getting out of it is 520 nanoseconds. So the architecture integrates the angle storage, residual angle computation, and the vector rotation within the SRAM fabric. This reduces the data movement between memory and logic, and it could potentially improve energy efficiency and the throughput. As observed, the simulation results, the residual angle is correctly converging to 0, and the accuracy of the vector rotation computation is also close to 96%. We have designed in such a way that we have a precise control of read, compute, and write in 3 different phases. This enables us for the scalability, and the design is picked here for 5 iterations. As we increase the number of iterations, we can see a higher precision. This application is used in the low power and area constrained systems and is very well suitable for embedded and neuromorphic computing platforms. Thank you.